We are continuing in 15.4, and in this section we're looking at analog to digital conversion. In the previous section we looked at digital to analog. Now we're going to be looking at the process of taking a analog input and converting it to a digital representation. So here we would have our analog input, and then on A or C, B, and A over here we would have our digital output. An analog to digital is the functional opposite of a digital to analog converter. An analog voltage or current is applied to the ADC input and is transformed into an equivalent digital value. Now, this particular circuit is called a flash analog to digital converter. And so let's talk a little bit about this circuit. We've already mentioned that we have an analog value coming in, and our goal is to convert it to a digital output. Now, this is a mighty 3-bit converter. Usually you would have converters that are much larger than that, maybe 16, 24 or whatever. But this is, again, this is where we're introducing the subject, and we want to keep it basic. So here we have the overall process, analog to digital, and so what we're going to do is start out with 24 volts, and we're going to put it across a Zener diode here, which will regulate to 10 volts, and so that 10 volts will be spread out across these components. Now notice it says R here. It doesn't give you a value of R, but all of the R's are the same value. So that 10 volts is going to be distributed in series across these 8 components. So if we took 10 divided by 8, we would have 1.25. So it will be 1.25 volt increments across these components. So if you notice here, down here, this is ground. Then we start at 1.25. We add 1.25 to 2.5, add 1.25 to 3.75, and so on, up to 8.75, and then there's 10 volts right here. Now notice that these voltages, a reference from each of these is fed over to and this is a comparator. This is an Amp Comparator. And what these comparators will do is that if the input voltage exceeds this reference value, we'll get a high out of these comparators. Now, if the voltage is less than that reference value, we'll get a low. And then those values will be fed into the logic over here, and this logic circuit will take that value and convert it to its binary equivalent. So let's start out with let's pretend we have an analog voltage coming in here, and it is, we'll say it's 2 volts. And so it's going to come in, and 2 volts is right about here. And remember that 2 volts is coming in on this lead, so it is equally applied to every comparator. Now that 2 volts is going to be greater than this 1.25, so it will put out a 1 here. But this is 2.5 volt reference coming in right here. It is less than that, so this will be a 0. And so what will occur, there will be lows on all of these outputs. There will be a high only on this one. So let's see how this affects this logic. First of all, we have the C over here, and so we would have the low coming in here. It would go over here, so this would be a low. And so we're dealing with 3-bit logic. We're going to have 3 possible bits. The most significant bit is going to be a 0. Then let's keep going. Here we have several inputs coming in here. We have a 0 coming in here. We have a 0 here, which will be inverted to a high, and then we have a low coming in here. So a 1 and a 0 going to this AND gate will produce a 0, and then a 0 and 0 going into this OR gate will produce a 0. So our second most significant bit, B, is also going to be a 0. Then we come down here to the last set of bits here. Let's see, we have the 0 coming in right here. And notice these are exclusive ORs. And then we have a 0 coming in here. And we have a 0 coming into this gate. and coming into this gate again a 0, and coming in from, let's see, what gate is this one? It's connected here. Most of these are zeros, and then coming in here from, we have a 0 here, and last but not least we finally have a 1. Now remember, exclusive OR, they only put out an output when the input is either a 0 and a 1 or a 1 and a 0. If it's 0 or 0, 0 and 0, or 1 and 1, there's no output. So in this gate we have a 0 and a 0, that would give us a 0. Then we have a 0 and a 0 coming in here, a 0. 0 and a 0 here produces 0. 0 and 1 here produces a 1. The 0 and 1 here, now these are two different, this will produce a 1, and then the 0 and the 1 here, this would produce our 1. So here we would have our logic level of 1. Now that is if we had a 2-volt input. Now let's do another one, and this time let's put in a, let's see, and take note here, remember this is a 3-bit converter, and so with 3 bits there are 8 possible states, and that's including 0. Note that there are 1, 2, 3, 4, 5, 6, 7 op amps, so every possible value must have an op amp representation in this type of circuit. So let's put in another value. Let's go in, let's say we have an input value of 5.1 volts. And we'll send that in here, and that's going to be slightly greater than 5, and so that'll be 1, 2, 3, 4. So what we would expect is a binary 4. Now what I'm going to do, I'm going to change the pen color here just so we can separate out what we're doing. Let's make it black. Okay, and so now we're going to go in here, we're going to put in a an analog value of 5.1 volts, so that will, this comparator will go high, so we'll put a 1 here. In fact, all of these below will be high. Put 1s on all these, and then these above here will all be 0. So, given the fact that it's 5.1, the value should be 1, 0, 0. So let's see what we get when we do the evaluation. We're going to put a 1 here, which will feed over here to C, and that in fact corresponds to our 1 right there. But let's see what happens to B and C. So coming in here, let's see, we're going to come into this OR gate, that would be a 1 there, and let's see, we have coming into, let's see, 1 there, and then from here again we have a 0, and that would inverted to a 1. And then from down here, now we have a 1 coming in here. And let's see, we do have a 1 coming in here. And we had a, oh, excuse me, there's the problem. At 5, actually, this is not a 0. This is a 1 right here. So we have a 1 coming that's going to make this a 0. And so 0 and a 1 will give us the 0. And let's see, did we actually have a coming in here? Wait a minute, what do we have coming in here? This should be a 0. Did I call it a 1? Because that is coming on from here. Wait a minute, let's see, what do we got? Coming in, this is a 0. So, evaluate. 0 and 1, 0. 0 and 0 going into the OR again. Here we have a 0. Now you got to really watch yourself when you do these. So, too many values. Okay, so the next one, last bit. We would have a 0 here, and on this input we would have a 0. And coming in from here, okay, we have another 0. And coming in from here, now this right here, we're going to have a 1. And coming in here, we're going to have a 1. And from here, there'll be a 1. And from here, there'll be a 1. So let's evaluate. Okay, a 0 and a 0, we're going to have a 0 here, and a 0 and a 0 here. This will make a 0. And then we have a 1 and a 1 coming out of here, but that's going to be, again, a 1 and a 1 is a 0, and a 1 and a 1, that is a 0. So 0 and 0 make a 0, and it looks like a 0, 0 makes a 0, and a 0, 0, so we have all zeros. So this gets really confusing very quickly, but you can see that when we put that 5.1 volts, that will equate to a binary 1, 0, 0, which is what we would expect. Now, this next picture here, this is the actual circuit that we just looked at. This is from Multisim, and I encourage you to go there and actually use this circuit. What you'll be able to do, you'll note up here there is a variable component, and you can press the letter A and it will change the value of this component. Now what this does, notice this is the voltage that is being applied as the analog value that we're evaluating, so you can set this to any of those analog values between 0 and 10, and you should be able to illuminate the light bulbs that are attached to the three logic levels indicating the 3 bits of our possible outputs. And so A will, I think A makes it goes down, and then if you press the shift key in A, it will make this value go up. So what I have done, I went in and I set this value to just over 5 volts, which would be right here, and this would equate to the binary 100 that we looked at on the previous screen. And you can see here we have a 1, 0, and a 0 indicating that binary 4. Well, this has been a quick introduction to the whole concept of analog to digital conversion. And as I mentioned earlier, these circuits can get quite complex due to their sizes, and this is only a 3-bit converter, and these will often be much higher bit ratios, and this is just one way of doing analog to digital conversion. There are other methods.